In the name of Almighty Allah, the most gracious, the most merciful. As Muhammad, peace be upon him, narrated, if anyone travels on a road in search of knowledge, Almighty Allah will cause him to travel on one of the roads of paradise. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your wonderful support to make the channel a grand success. We are a family, a partner. Please subscribe and share our channel if you haven't done so far. We as a team can work together to convert challenges into opportunities and opportunity into success stories. These success stories can be monetized into value addition in the world by large. Thank you very much. Today I'm going to discuss my lecture number 21, oil and gas productions, exploration, production, upstream, midstream, refining, petrochemical, differentiated performance, enabling profit optimizations, lecture number 21. Okay. Before my lecture, I used to read a Quranic verse, Qala Rabbi Shrah li Sadri wa Yassar li Amri wa Hlul Uqdatam min Lisani Yafqahu Qawli Allahumma Rabbi Zidni Ilma. O my Lord, open my chest and ease my task for me, and loose a knot from my tongue that they may understand my sins. Allahumma Rabbi Zidni Ilma, O Allah, advance me in my knowledge and true understanding. Okay. So, oil and gas productions, introductions, facilities, process, reservoir and wellhead, upstream facilities, midstream, refining, petrochemical, utility systems, unconventional, conventional resources and environment effects. Okay, what is ultimate goal? We have planned to deliver shaping the clean and sustainable global energy and plan to deliver 300 lectures, more than 300 lectures next couple of years. Oil and gas productions, the midstream facilities, lecture number 21, LNG. Okay, key take. Okay, key takeaway points, lecture number 21. Facilities, process, onshore, offshore, LNG process, LNG liquefaction methods, ConocoPhillips, SMR, PRCO, C3MR, Shell DMR, dual mixture refrigerant and lint. So today we are going to discuss. Okay, LNG process operations. LNG is a gas or transport product. The gas, which is primary methane CH4, is converted to liquid form for ease of storage or transport, as its volume is about 1/600 the volume of natural gas in the gaseous state. It is produced close to the production facilities in LNG liquefaction plant, stored, transported in cryogenic tanks on an LNG carriers, and delivered to an LNG regasification terminal for storage and delivery to the pipeline system. LNG carriers are used when the transport distance does not justify the cost of the pipeline. The main drawback is the cost of the liquefations, calculated as how much of the total energy content of the gas is used for liquefations. About 6% of energy content is used to produce LNG in a large modern plant due to overall thermal efficiency. More than 10% could be consumed with a smaller gas turbine driven trains. This compared to losses of about 0.9% per 1,000 kilometers of transport distance for a large pipeline system. This comes from a gas plant as outlines. It must satisfy a sales gas specification. Ethane, propane and butane all have a freezing points of less than minus 180 degrees C and can be part of the LNG, but the concentration of methane is generally above 90%. Some NGLs are also needed as a refrigerant for the cryogenic process. Okay. Now LNG liquefations. How it's happened? LNG processes are generally patented by large engineering oil and gas companies, but are generally based on a 1, 2 or 3 stages cooling process with a pure or mixed refrigerants. The three main process type of LNG process with some example of process licenses are: first is a cascaded cycle, second is a mixed refrigerant cycle, third is an expander cycle. Okay, the first cascaded cycles, it's a separate refrigerant cycles with propane, ethylene and methane that is introduced by ConocoPhillips. Second is a mixed refrigerant cycle. First, a single mixed refrigerant SMR, TRICO, single mixed refrigerant LIMOM, Linda. Third, a propane recooled mixed refrigerant C3MR, sometimes referred to as APCI, air product and chemicals. And number fourth, a shell dual mixed process that is called the DMR shell. Okay, dual mixed refrigerant liquefying hexenes and mixed fluid cascade process MFCP, state oil and Linda introduced. And the last is the expander cycles, that is a Crockett EXP process. Each process has different characteristics in scalability, investment cost and energy efficiency. For smaller installations, to handle a standard gas or accelerated small gas fields, a single cycle process is preferable due to its low capex and possibility lower weight for the floating LNG, even if energy efficiency is significantly lower than the gas cascaded or DMR process, with cost more but also allow the larger strain, a typically 7.8 million tons per annum and lowest energy consumption per energy unit LNG produced. Design. Mixed refrigerant design. Most processes are a mixed refrigerant design. The reason is that the gas has a heat load to temperature Q over T curves that, if closely matched by the refrigerant, will improve stability, throughput and efficiency. If you can see in the picture, the curves tend to show three distinct regions matching the pre-cooling, liquefaction and subcooling stages. The refrigerant gas, this is my subcooling, liquefaction and pre-cooling. Okay. The refrigerant gas composition will vary based on the individual design as well as the power requirement for each state, and is often patent, location specific combination of one or two main components and several smaller together with the careful selection of the compressed pressure and expanded pressure of the refrigerant to match the LNG steam. Okay, typical LNG train power uses about 28 megawatt per million tons of LNG per annum, MTPA, corresponding to the typical 200 megawatt for a large train of 7.2 MTPA or 65 megawatt per stage for the 3 cycles. In addition, other consumer in the gas treatment and pre-compressions add together the power consumption and bring into the sum 35 to 40 megawatt per MTPA and over 50 for a small LNG facilities well under 1 MTPA capacity. Some examples are given as we can see here. So if you can see here, as we illustrated, the complete design, all designs are shown that the exchanger to be seen comparison. This is the generally needed for the high capacity, but for smaller plants, air for the heat exchangers are normally used. Okay, triple cycle mixed refrigerant cascade. A triple cycle mixed refrigerant cascade claims to have the highest energy efficiency. It is represented by the lean design, a code developed with state oil. The actual design varies considerably with different process. The most critical components is the heat exchangers, also called the cooled box, which is designed for optimum cooling efficiency. Design may use a separate cooled boxes or 2 or 3 cycles may combine into one complex common heat exchangers. This particularly designs use the patent linked coils of wound heat exchangers, also called the rocket design, due to its exterior resemblance to the classic launch vehicle. For each train, the cooling medium is first passed through its cooling compressors, since pressure times volume over temperature PV over T remains a constant. Its result in the significant temperature rise, which has to be dissipated typically in seawater heat exchangers. So it demonstrates where we are. It then goes through one or more heat exchangers, cold boxes before it expands. Either through the valves or the turbo expander causing the temperatures to drop significantly, it is then returned to the cool its cold box before going onto the compressor. On my next slide, we will discuss a pre-cooling, liquefaction and subcooling stages as we have demonstrated here. Pre-cooling, liquefaction and subcooling. Okay, pre-cooling, liquefaction, subcooling. The pre-cooling stage cools the gas to temperature of about -30 to -50 degrees Celsius. In the pre-cooling or cold box, the cooling elements generally propane or mixtures of propane and ethane and small quantities of other gases. The pre-cooling or cold box also cools the cooling medium for the liquefaction and subcooling stages. Number 2, liquefaction process takes the gas down from -30 degrees Celsius to -70 to -25 degrees Celsius, typically based on mixtures of methane and ethane and other gases. It cools the LNG streams as well as the refrigerant for the final stage. Number 3, subcooling serves to bring the gas to final stage LNG stage at around 162 degrees C. The refrigerant is usually methane or nitrogen. Okay, for next slide, we will discuss a ConoFlip's optimized cascade process. Okay, as we have discussed earlier, the ConoFlip's optimized cascade process was developed around 1970. It has 3 cycles with a single refrigerant gas. First is propane here, propane cycles, ethylene and methane cycles over here. Okay, so gas, propane, ethylene and methane in each stage. So this is my LNG and this is my treated gas. Convert and deliver what we have planned. In my next slide, okay, Shell DMR and APLI C3MR design. The dual cycle mixed refrigerant, that's DMR, developed by Shell and others, may look similar, but they different as per the requirements, as multi-stage compressors are typically needed. If you can see here on my right hand side, that is a C3MR on the right, and this is my DMR, a dual mixed refrigerant design. So as we have discussed earlier, it is more efficient compared to other design. Okay, now we are going to discuss SMR and LIN. So for a small and micro LNG, single cycle design are often preferred. There are literally hundreds of patent solutions, but only a handful of the mainline licenses but have solved the challenge of the achieving single cycle refrigerations. However, this means a multiple internal stages in the process of flow and the heat exchangers itself. The PRICU SMR, if you can see on my left hand side here, and the other is a linked aluminum, so that is on my left hand side. So that is providing a solution for a smaller or single cycle design for refrigeration purposes. Okay, storage, export and regasification. Storage at the terminal and on LNG carrier is done in cryogenic tanks at atmospheric pressure or slightly above, up to 125 kilopascal. The tanks are insulated but will not keep LNG cold enough to avoid evaporation. Heat leakage will heat and boil off the LNG. Therefore, LNG is stored as a boiling cryogen, which means that the liquid is stored at its boiling point for its storage pressure. So atmospheric pressure, that is about -162 degrees C. As the vapor boils off, heat of vaporization is absorbed from the cools the remaining liquid. The effects is called auto refrigeration. With efficient insulation, only a relatively small amount of boil off is necessary to maintain a temperature. Boiling of gas from the land-based LNG storage tank is compressed and fed to the natural gas pipeline network on LNG carrier. The boil of gas can be used for a fuel purpose. So if you can see over here, we demonstrate the LNG terminal process overview. Okay, at the receiving terminal, LNG is stored in a local cryogenic tank. It is regasified to ambient temperature on demand commonly in a seawater heat exchangers and then injected into the gas pipeline system. Okay, conclusion. Today we have discussed LNG process, cascaded cycles, mixed refrigerant cycle, and expander cycle. Okay, next topic, oil and gas production. We will discuss refining facilities. Okay, references: Qatar Petroleum Doha Qatar, Oil and Gas Development Corporation, World Energy Outlook 2013, US Geological Survey, US Department of Energy, Shell mergers oil field, Information Energy Agency IA, Wikipedia Oklahoma, State Oil Fact Sheets, North 6 Standard Norway, The Story of Oil in Pennsylvania, A Liquid Gas Encyclopedia, Natural Gas from Wellhead to Burner Tip. Please do not hesitate to send me your feedback t.masood.dr@path.edu, or you can also send me through WhatsApp. I have provided my numbers. Together, everyone achieve more. Please stay at home, stay safe, inspired, and blessed.